Good morning, friends. I am going to discuss regarding ammonia and urea plant. What is the need of ammonia and urea? Basically, fertilizer is the basic need to grow vegetables and agriculture needs. So these fertilizers provide the nitrogenous component to the soil and which ultimately catalyzes the process to produce good quality vegetables. Some vegetables are uprooted on the ground, some are inside the ground. So this nitrogen component, which is a basic raw material for soil to become a fertile. So we as a chemical engineers, we are in the process industries. So we make ammonia, we make urea. Normally in India, urea is the final product which goes to the farmers. But in some places, ammonia is directly used to supply the nitrogen supplement. So as ammonia, formula is NH3, where one component of nitrogen and three component of hydrogen. So how this ammonia forms? So it's as very clearly understood by the formula NH3. You need nitrogen and hydrogen. The hydrogen we get from natural gas and nitrogen we get from atmosphere because nitrogen is available in abundance in atmosphere, and you go by the atmospheric analysis, 79.8% nitrogen is existing there, oxygen is around 20%, and some quantity of CO2 is also there. So natural gas is the raw material for any ammonia plant or methanol plant. Earlier to natural gas, naphtha and other carbon hydrocarbon process are also available, but natural gas is basically a clean gas and in which methane is the dominant component. Depending upon the composition, if methane is low or high, we call the natural gas lean or rich. So basically natural gas is a complete set of hydrocarbons in which we have C1, C2, C2 means ethane, C3 propane, C4 butane. In butane also we have I component and neo component, I butane and N butane. So it's a mixture of all. The basic thing is that if C1 is high, then gas become lean, and if C1 is less and C2, C3 higher hydrocarbons are more, gas is rich. Basically this lean or rich is defined on the basis of heating value. How much heating value we will get from the particular gas if we burn it. So this lean and rich term is to define the gas quality, and that comes from the component. If higher hydrocarbons are there, we will get more heat. If less hydrocarbons are there, higher hydrocarbons, then we will get less heat. In natural gas, we are having some impurities also, which is not desired in the downstream product, and it can affect the health of the catalyst, which is the critical component for reforming and other things. So sulfur is normally in the range of 10 to 50 ppm. Ppm means parts per million. So 1 part in 10 to power 6. So this is ppm. So this sulfur is basically poison for the catalyst used in the ammonia system. Catalyst means in some catalyst process we have hydrotreater where nickel catalyst is there. reforming we have, and then finally we have a converter. But in latest ammonia plants, we have pre-reformer and pre-reformer guard also. The basic purpose of this pre-reformer and pre-reformer guard is to reduce the heat load on the reformer. Nowadays, we are having three types of process. Earlier process was known as brown, then next is blue, and then finally green. As the word green simply signifies, if you have a very less emission or zero emission, you can consider the process as a green process. And if you have relatively more emission but less emission than the brown process, then it is blue. So our old conventional plants are normally comes under the category of brown. So we can ask or we can call them as a brown ammonia or brown urea or brown methanol. The thing is that how much gas in the form of flue gases going into the atmosphere, which can lead to carbon CO2 in the atmosphere. So protect the environment in globally. Now the concept of green ammonia, green urea, green methanol is coming into the market. It is well known that natural resources are limited. If we will utilize them properly, then we can hand over it to our next generation. Otherwise, we will do injustice to our next generation. So, environment protection, like a safety, is everyone's responsibility. Similarly, environment protection is also everyone's each individual responsibility. And anything which is responsibility it starts from home. So if you are keeping your home place clean, you are not polluting the land, you are not polluting the atmosphere. So this pollution normally in the form of air, land pollution, air pollution, water pollution. So if you are not discharging something bad chemicals into the water which is going into the drain channel through your sewage system, then you are doing some justice to the environment. And ultimately, this environment will come back to you. Today you are thinking you are polluting the environment, but then you are getting in return by paying in terms of medicines, because you cannot exclude yourself from the environment, and environment is the global. And that's why protection of environment, because there is you cannot fix any boundaries into the environment. You cannot make a wall. Okay, this side of environment is green and next side of environment is bad, and I will pollute it and another person. So whatever pollution either by you individual or others, all will be a common. So if someone is doing injustice to the environment, the prima facie problem will be faced by everyone. So that's why nowadays these developing countries have been taught to protect the environment. Similarly, all the developed countries, they are giving some sort of uh, uh, financial help or some lucrative offers to protect the environment, make your process CO2 generation from the system less. And their Geneva summit was also there. So carbon decarbonization is the future need, and it will come to us. So that is another part. Right now, I am going to concentrate more on the ammonia and urea process. So as I told, sulfur is the undesired component available in ppm range. So depend upon the gas quality, it can start from 1 ppm, 2 ppm to 50 ppm. If more sulfur means you need more zinc oxide bed, and then replacement of the bed will be frequent. And our final target is to reduce the sulfur to level of 0.05 ppm. So what is the process? When natural gas is coming, it is mixed with hydrogen at a pressure of normal, you can say 35 or whatever gas pressure is available, 30 to 35, and at a temperature of 390. Nickel molybdenum is a catalyst, so which converts this natural gas in presence of hydrogen to H2S. Sulfur can be organic or it can be inorganic. So normally we have analyzers at the inlet of the hydrotreater and at the exit of the hydrotreater to ascertain how much sulfur is available in the NG and how much it is available at the hydrotreater outlet, and similarly one at the desulfurizer outlet also, whether we get the required ppm level prior to sending this gas to the catalytic beds in the downstream. So this H2S is then absorbed on zinc oxide bed, where this sulfur got absorbed on, this is adsorbed not absorbed. There are two different terms, absorption and adsorption. So this adsorption took place and then it converts into zinc sulfide, and then zinc sulfide gets slowly deposited on the pores of the catalyst. In old, normally two beds of zinc oxide were normally used. One is lag, one is lead. So the thing is that depend upon the inlet concentration of the sulfur, life of the zinc oxide bed will be there. Normally depend upon the inlet concentration of sulfur in gas, height of the zinc oxide bed is decided, so that between two shutdowns, one is normal shutdown and one is plant shutdown. So now I am talking about the plant shutdown. Some companies follow 3 years norms, some company follow 4 years norms. So that is called turnaround. So you can change this catalyst only in turnarounds. If you have proper system of double block and bleed system, then individual bed can be changed online with all safety precautions, and then it can be taken in line also. For that you should have a proper heating system, lineup system and isolation system, because the system will be operated at a pressure of 30 to 35 bar, and if you don't have proper isolation, it will be risky to unload the catalyst and then load the catalyst, then take the catalyst bed again in line. So earlier this was alone Jadon bed, but nowadays one more level at the bottom of the lag Jadano bed is available, and this is normally around, suppose total catalyst in one bed is 30, so one fifth or one fourth, one small bed, you can say final refinement bed is also there. Lot of catalyst suppliers are in the market, like Johnson Matthey is usually having Pura spec. Similarly, Topso is having S, some number is there, 201 I think, what I remember. So this all gives the final refinement, means first level of refinement through Zn, so that this sulfur will reduce to 0.05 or something, and then finally it will go to 0.01 level. So this particular bed, which we can say efficiency bed, which is around 20 to 20% of the total bed, this need reduction. This is not normal Zn. You can just put the catalyst. For this you need a reduction, and that is achieved by the hydrogen. If you are having a hydrogen in the system, then it is good. If you don't have, then you have to brought the hydrogen cylinder, and that hydrogen cylinder requirement will be calculated based on the reduction process. And normally this catalyst suppliers are normally provided these guidelines, otherwise you can do this calculation also. Then once this gas is free of sulfur, then next level is that this is going to the reformer. So reforming basically is natural gas in presence of steam. This steam is not in this is in the form of gas. So this Ng plus steam, and this converts this natural gas into CO, CO2, hydrogen. So if higher hydrocarbons are more in the system, then normally we, to avoid load on the reformer, we provide pre-reformer guard and pre-reformer also. So where same nickel catalyst will be used, and but the thing is that higher hydrocarbon means C2 to higher C3, C4, that will be converted into methane, and then finally this methane along with CO, CO2, hydrogen will go to the reformer. So typically reformer temperatures will be in the range of 520 to 620 inlet temperature, and outlet temperature will be 760 to 860. In ammonia plant normally it is in the range of 780 degree, and in methanol plant it is going up to 875 also. So in reforming we are using this nickel based catalyst, that is alkali on the supported on alkali, and it is not full, some other components also there. Typically you can say around 15% nickel is there, but normally this data you can easily get from MSDS, that is material safety data sheets, where it will tell all the quality handling procedures, because nickel and other components, one has to handle with care, because if dust of the nickel can be a cancerous also. And in this process of reforming, one liquid nickel carbonyl also formed, that is also very deadly, and presence in the system can be ascertained by a special analysis of the condensate at the local drains. So this problem has to be tackled very in a safe manner during the shutdowns, because all the condensate which are in the drain pots or drain legs, that has to be taken out, and it should not get exposed to the operators or men, casual contractors. Normally the persons who are working in the process, they are aware of the hazards, but it is our moral responsibility that hazards should be properly communicated to the contractor or the casuals or the non-technical people if we are taking them into the process area. So as I explained, this reforming reaction which converts this natural gas into CO, CO2, hydrogen. So steam is normally used in the ratio of 3. There is some threshold value that steam S by C can be minimized also. So now latest upgradations are there. This lower the S by C ratio, efficiency or energy requirement of the plant will reduce. Sorry, efficiency will be improved, and the plant, this energy requirement will reduce. But one has to be very careful if there is some limiting, and if steam by carbon ratio comes below certain limit at higher temperature, carbon laydown can result in the failure of the complete process. At carbon laydown on catalyst will cause high delta P, and then hotness of the tube and failure of the tube also. So what is reformer? Basically this reaction is endothermic reforming reaction. So in reforming reaction is endothermic. So what we are doing, we are supplying heat to the reaction with the help of external burners. These burners are fired with Ng plus the gases which are coming from the waste recycled gases. So complete mixture at a particular temperature in presence of hot air is going to the burner. So for any reformer, the burner and tube, so this ratio between tubes to burner is normally 2.5 to 3.5, and tube length of the reformer is normally in the range of 12 meter to 13 meters, and because it's a high temperature zone, so metallurgy of the tube is also should be good. So in this earlier tube was HK40, then in conal tube has come, and then now microalloy is there. So what is this? Nickel and chromium and niobium is there, concentration are changing, and now some good additives we are adding to have the better life of the tube, that it should not fail, creep, any hotness. So, and the dia of the tube, ID you can say, it is varying from 100 mm to 125 mm, and thickness in the range of 10 to 12 mm. Lesser the thickness, better the heat transfer, and less heat requirement. But it is a balance between the optimum. And for the tube health, we have one monitoring system called tube wall temperature, which tell that what is the skin temperature of the tube when this reforming reaction is taking place. So normally the design temperature of the tube is in the range of 1000. So if temperature design is 1000 for a certain particular pressure and temperature, then our operating range will be around 100, so that operator should have a safe operation. So if 1000 is that, then normally 875 to 900 is our operating range. So this temperature measurement will be done by the operations as well as CMI conditioning monitoring if people are there. So they are the like a third party checking. So every shift, or normally in the night shift, operators are doing this tube wall temperature measurement to know the health of the tube. Physical observation also tells the condition of the burner as well as the tube. So this reformer can be top fired, bottom fired, side fired, and terrace fired. So depend upon the type and requirement, the reformer is normally designed. So reformer reaction I told you is endothermic, and at the outlet of the reformer we got methane in the range of 11 for ammonia plant, and 2.7 to 2.8 or up to 3 for methanol plant. And temperature I told you for ammonia normally is in the range of 790, and for methanol plant it is in the range of 850, 860 to 875. So it's depend upon different type of process are there. Halda Topso process is there, Uday process is there, and now autothermal reformer also comes in market. Uh, so in ammonia process, we are having two type of reformer. One is primary reformer and one second is secondary reformer. The concept of secondary reformer is to introduce air so that we can get required nitrogen, and it like a reformer is having a multiple burners. Some reformers are having 256 burners, some are having 140 burners, but secondary reformer is a single burner where high temperature air is getting introduced, and then this reforming reaction heat is supplied by the combustion of the air. You can understand this as a control explosion also, although this word explosion you should not get confused, but this secondary reformer reaction is basically controlled explosion where oxygen is introduced at high temperature, and then this combustion take place, and the reformer outlet, secondary reformer outlet temperature increase up to 980, and methane slip reduced from 11 to zero point 0.3. So this high temperature we utilize in reform gas boiler. So what we are doing, we are putting this into the tube side, because this is at the high pressure. Sorry, gas is in the at the pressure of around 30 bar, because typically reformer delta P will be 3 to 4.5, and type of catalyst loading, it can be a single type of catalyst, or sometimes vendors are providing a mix. 33% of the tube will be have one type of catalyst, and another 33 will be different, sometimes 50-50, or sometimes single catalyst also, like a, and catalyst type will be also different shapes. Some are having 7 holes, some are having 4 holes, and some are having 4 holes with edge configuration. This all actually required to give proper reforming on surface. Basically, catalyst is a surface phenomena. The effective surface available for reaction with respect to that catalyst is not brittle also. So that how to provide maximum surface area with without compromising the hardness of the catalyst, because in operation what is happening when plant is running and tripping, then this will experience high temperature and then low temperature, so there will be expansion and contraction. So along with the expansion and contraction of the tube, the material fill inside the tube will also experience some pressure, and if that pressure will increase to more than the desired limit, it will call crushing of the catalyst, and with the crushing of the catalyst dust formation will take place. And then what we will observe that in the process, the delta p means differential pressure across the tube. So it's a pressure at the outlet minus the pressure at the inlet of the tube. So if this is increasing, then there is always a limit, because increase in delta P will have introduced inefficiency into the system, and you will have energy loss. And it is not only energy loss, if it is increased to certain extent, like in a catalyst bed, there is a bottom, there is a support grid. So these grids are designed for some maximum pressure. So if this delta P keep on increasing, it will have an impact on the flow pattern. There may be some channeling also visible, and the thing is that ultimately it will have a pressure on the grid, and we cannot take risk to fail of the grid. If grid will fail, then this catalyst will come into the pipeline and then block the pipeline system. So in reformer also, at the bottom of the tube, the grid is there with the holes, which hole size is smaller than the size of the catalyst. So this grid is normally inspected prior to loading of catalyst, and then we are loading the catalyst. Earlier, in old times, it was loading through SOX system. Then accuracy will depend upon the skill of the person. Now it has come that automatic systems are there. Unidance and is the latest technology, and one more latest technology is there in which fixed amount of catalyst is going, and as I told, the reformer height is around tube height is around 12 to 13 meters. So you have to avoid the free fall also, because if any catalyst will fall from this height, it will break. So how to avoid this breakage, how to reduce the free fall height, mechanism are there. So basically what it is saying, it is like a rope with the springs at different locations. So when catalyst pellets are falling, it will fall on the springs, which will reduce its speed. Then it will go to the next one. So these springs are provided at different locations. So when catalyst pellets are falling, it is falling on first, speed will reduce, then it will go for another half meter or something, another spring is there. So this is all automatic. So when we are doing catalyst loading, initially this speed of the machine unidance method and other things are there. So it all depend upon how much you want to achieve. So normal, the standard deviation for entire reforming catalyst loading, that deviation should not be more than plus minus 5. But good companies as a practice want to go for more informed loading, so they are considering the fact plus minus 3. In this also tricks are there, means you are going for individual tube deviation or you are going for overall tube deviation. So you have to be very careful what parameters you are choosing to decide this deviation. So if during catalyst loading deviation is more, then there is no other option just to unload the tube. So you will lose the catalyst and time both, and then reload the tube. And the outage, this outage means suppose in 12 meter of tube, you are loading 11.2 meter, then 0.8 is the outage. This outage we are measuring for all the tubes to have the knowledge how good our loading was. and this outage will be a initial outage as a record, and when we will check this outage after 3 years or 4 years depending upon the turnaround duration, how much catalyst settled in 3 years. This catalyst settling will depends upon the number of startup and trips. More number of trips means settling will be chances is more. And what precaution we have to take is this outage should not reach to that limit where tube is getting exposed directly to the furnace condition. So normally this height is designed by a technology supplier such that in no case this will go below to the final limit where the tube will be affected. And these tubes normally supported by the spring hangers, so that in case of heating, what will happen, tube will expand vertically upward or downward depending on the design of the reformer. And this reformer is hard because you can understand the cost of the full plant, maybe 40 to 50% cost is around the reformer only, because reformer tubes, then convection section, IDFD, then reformer outlet temperatures going to the transfer lines. As the temperatures are high, so this transfer lines material may be CS, but it are having a refractory line. Even furnace of the reformer is also refractory line in the form earlier bricks were used. Nowadays castable bricks, casting, or maybe Sarah blanket, depend upon the type of the technological suppliers, and their effects are there. This refractory process, its application, drying out, all are very skilled process, and it has to be done under the OEM or vendor, because if it is not done properly, then you have a hot spot. Hot spot means ki inside temperature of the reformer, I told you, for flue gas may be in the range of 1000. So, and our this metal box temperature, which is CS, normally can sustain up to 250 or 300. So if refractory will fall, that is a protection between the wall and the flue gas condition, then this become red hot, and in that case if it will go extreme, it can fail also. So normally to contain the flue gases hot condition, normally the furnace is operating below the atmospheric condition, normally minus 5 water column. And we have a different type of furnaces in which some are forced furnace, some are induced furnace, but this combination of induced and forced is the best one, and it has been practiced. And normally this reformer will be provided with a various tip logic, like draft condition should not go positive, so draft pressure will be there. For combustion air means air supplying to the furnace, as well as reformer outlet temperature also there is a trips nowadays provided, and this all trips are provided 2 out of 3, with the sill levels 1 to 3. So depending upon the criticality and how much you want safety and how much budget you have, so all will define the this sill levels. Good plants are going with a proper sill level, and this all comes under different job, GHA, and then revalidation of agile if plant is old. So that is another topic which required a specific skill. So at the reformer, I am coming back to the reformer. So a reformer, like a big reformer, suppose it is, then burners, suppose I told you ratio is normally 2.5 to 3.5. So burners are in the range of 100 to 256. So suppose 256 burners are there, then it can be 16 into 16 means 16 rows are there. And in if number of tubes are suppose 500 or 800 or 840, suppose 840 is there and 16 rows are there, then it will be like a 56 tubes in one row, and for that 16 burners are there. So for 16 burner take care of 56 tubes, so that will be decide at what distance the burners are. So and the burners which are inside, that are having different heat duty, and which is at the end different. The basic reason is that extreme end will see the one side of the tube, and in between will see the two sides of the tube. Means if burner is there, one tube is this side and one tube is this side, so this particular burner will give heat to two tubes. But if it is at the end and the tube is here, so this burner will show the see the only one side of the tube. So these burners which are at the ends, extreme ends of the furnace, are having low heating value, maybe 1.7 megawatt, like that, depending upon the heat requirement, total heat requirement. This is distributed, and which is in the center will be around 2 to 2.5 megawatt. Other than this burner, which this is called arc burner, sometime we are providing additional burner which we are calling tunnel burner. So this all depends. When additional heat is required in the convection section, then tunnel burners are used. After that tunnel burner, there is another burner called superheater, because we produce steam which has to be superheated for the purpose to avoid the condensation. So we are having superheater burners also in the convection section. What is convection section? Basically, whatever the combustion gases are there, that is at high temperature. So we need to utilize the heat of these high temperatures, flue gases. This is going through the convection section where series of coils are there, and where this heat is getting utilized, and finally the gas which is going to the atmosphere will be in the range of 120 degree, and then it will come at the suction of the ID and goes through the chimney. In chimney effect, maybe you are aware also that if temperature is high, then what will happen, this become lighter, and if temperature is more less, then it will be heavier. So what is happening, when hot gases are coming, due to the density difference, it lifted to the atmosphere automatically. So normally chimney's height of the ID will be around 30 meters or 40 meters. This is also all depends upon how much we want to protect the environment. So because if you increase the chimney height, then certainly the load on ID will increase. But same way, you are discharging the gases to safe location. Heat, at least 120 degree heat, you are with a huge amount of 7 lakhs or whatever gas, flue gases quantity will be there to the atmosphere. In this nowadays we are using good quality low NOx burner, because this NOx, NOx and CO too. There are CO limits. The CO basically goes for the incomplete combustion. So for NOx, nowadays the environment limits is 150 ppm and CO is 50 ppm. So earlier old burners were NOx were 300. So this NOx formation also depend upon the temperature and mixing in the burner. So burner quality should be also good, and there is a primary and secondary air into the burners. So if and this burner blocks are damaged, then it will have a poor combustion that can be seen with the help of CO or explosive into the flue gas section analyzer. And if burners are not good, it can cause impingement on the tube, and this impingement on the tube is very dangerous for the tube, because if suppose in running tube will fail, then what will happen, this all the natural gas in a huge quantity will come all of a sudden into the furnace block, and you don't have that much burner which can completely combust this gas. So what will happen, this will make an environment for explosion, and in that case normally operator has to immediately stop. But the stoppage is can save the plant safety point of view, but again downtime of the reformer will be very high, because you need to replace the tube. It may be tube is available or not available, so that's why normally the plants are keeping certain percentage of tube as a standby, not a standby, sorry, as a spare in workshop, because standby option is not available. Sometime there is method, you can nip the tube inlet and outlet, and you can proceed with the plant operation also. but that is not an available option for all the plants. And it depends upon the number of tube failures also, because suppose if any tube is hot or something, if you want to isolate, it's a group of tubes, so you cannot do it also sometimes. Normally what we are doing, if we are seeing that tubal temperature is high, we throttle the individual burner which are providing heat to the particular tube. So furnace inspection is required to for the reliable operation and safe operation. It is not only reliable, it is safe also, because furnace, he is having a huge gas, and for that in under PSM, process safety management, they calculate if suppose any failure of the reformer, in how much periphery this gas will go and do the problem. Problem means ki gas will spread, it will form combustible environment, and so it will affect the persons who are working nearby. So nowadays systems are getting automated, so number of people available at a time around the furnace is going less and less. So this will reduce the severity level, and accordingly under the PSM guidelines, we are doing lot of efforts to provide the automation, so that in case of any emergency or any failure, things cut off automatically. So after this secondary reformer, when methane come down to zero point 0.3, and it is passed to RG boiler, where we generate high pressure steam. High pressure steam means normally in the plant we are having three level of steam. Low pressure is 3 bar roughly, medium pressure is 30 bar, and high pressure is 110. This 110 steam that what we are generated is normally used to run the high pressure steam turbine. Steam turbine basically, because power requirement, if you thought of in normal plant of ammonia capacity, suppose it is around 2200 metric ton per day, then in case in gas compressor if you have, then it may be around 35 megawatt to 40. So this is huge requirement for the power also. So normally for reliable operation we are going with that turbine. Turbine can be different type. Some are let down turbine, means high pressure steam to medium pressure steam. Some are let down plus condensing also. Some are directly condensing. So depend upon the requirement and steam balance across the plant, we are going to for that particular type of turbine. For ammonia process, this RG boiler outlet temperature 360, then it is going to shift reactor. The shift reactor basically what is it doing? It is converting this CO to CO2, because CO2 is the required for the urea form, and nitrogen already we have introduced into the secondary reformer. So we get the mixture of CO2, hydrogen and nitrogen which is required for the ammonia. So this CO we are converting into HTS, then we are sending it to LTS, low temperature shift converter. This HTS means high temperature and LTS is low temperature. So ultimately what we are doing, in like 12% or 13% CO at HTS inlet will go to further reduce to 3.17, and after LTS it will go down to 0.3% CO. And then whatever CO2 is generated, we have a different absorption system that use GV system or some other. In that also, our old system was having HP and LP regenerated, but now semi-lean concept also come. So the CO2 which we take out with have, and when it is get washed, so CO2 slip, this system which is HP and LP will be have a CO2 slip in the range of 0.1 mole percent, and with semi-lean it has come down to 200 ppm also. So more the slip, you have a loss of ammonia production. So and so less the slip, you have gain, and less the slip, then you will generate less inert in methanator also. What is methanator? Basically whatever CO2 slip left out, it is converted into methane, which will be again act as an inert into the system. So after the methanator, we got the synthesis gas, and then this gas is fed to converter, ammonia converter in the ratio of 3:1. three will be the hydrogen and nitrogen will be the one. So normally ratio we are maintaining close to 2.85 something. So hydrogen become a limiting factor. So this converter because operates this as I told ki ammonia 3 hydrogen plus nitrogen. So 4 moles convert to 2. So there is reduction in moles. So we need higher pressure for favorable reaction, and this is exothermic. So lower temperature will be favorable. And third will be the composition. So we have to minimum ammonia at the inlet of the reactant. So that means we have to whatever ammonia formation will take place, that has to be removed, and in recycle you should have a minimum ammonia so that have a favorable reaction. So high pressure, optimum minimum temperature, and low concentration of ammonia in the inlet reactor is the favorable condition for the converter. Converter may be two stage, and what it is doing when this ammonia and hydrogen got mixed, it forms ammonia. Lot of heat is generated, so that is having adiabatic plus isothermal combination. And what we are doing, the exit temperature we are utilizing, intermediate beds are there to heat the inlet temperatures, so that the heat requirement will be reduced for the converter. And initially when we are starting the plant, it is supported by the startup heater, and once reaction get stabilized, then we are cutting off the startup heater and then reaction is going out. So in normal operations we have to be very careful with the hot spot. If in case of due to the inlet temperature drop or concentration drop or inert accumulation, if hot spot is reducing, operator has to be very careful, because if he is not careful, it can cause a quench of the reaction and then full process will go to shutdown condition. So this ammonia at high temperature will be in the gas form, and to we need to cool down in subsequent sections to take it out. So this once the ammonia in the liquid form is taken out, whatever the left out gases, it is again recycled back and fed to the converter. And normally this fresh makeup is around 1, then recycle will be around 3 to 4 times. So compressors normally having a LP compressor, HP compressor, and final stage is recycle. Recycle compressor is for very low compression ratio, but here in LP compressor means suction is suppose 17 bar, then first stage it will be 40 bar, next stage it will be 80 bar. So depend upon the type and requirement. So in some planted this are operated up to a pressure of 250, then you may have three stages, or you may have reciprocating compressors to achieve those. So depending upon the process, type of compressor and everything will be decided. And to achieve the efficiency, we are having intermediate cooling between the compressor to have a isothermal stages, because if you don't have isothermal stages, then inefficiency will be very high. So once this liquid ammonia is separated, then that is sent to the urea plant, and CO2 is also sent to the urea plant at a pressure of 0.6 to 0.7. So this CO2 and ammonia will be a raw material for the urea, which in reactor gets converted into urea carbamate, and this urea carbamate it further decomposes into urea plus water, and then this water is slowly getting concentrated, and finally when after the vacuum section we got the concentrated urea molten, which can be fed to the clearing tower. Nowadays old system is clearing tower. Nowadays granulation urea also in the market, and for more productiveness, coated urea like neem coated urea also came in market. So for today, this is I would like to close here regarding the ammonia, urea. In another session, I will take the urea process separately. And if you have any doubt, you can mail me. I will, and or you can put a question on my YouTube blog. I will take my time and try to give you full justice to your questions, whatever query you have. Uh, my intention is just to familiarize the people, because this process has developed in maybe 100 to 150 when topso and haber process comes in market, and then slowly it has gone to this limit. And to understand this process, I also took around 32 years, and still I cannot say ki I fully understood the process, but I can say ki I have that level ki you can understand maybe 90% I have already gone, 10% scope is there, and I am not stopping my learning. I am still going to the latest technology, vendors meetings, seminars, others, and whatever I am gaining, I like to share. I thought ki it is a good to share the things to the newcomers or to the already people who are experienced also, to help them out, uh, so that the knowledge cannot be contained within me only. I want to share it for the general interest. Thank you. Namaskar.